maximal symmetry, and consequently a space of constant curvature whose curvature can depend upon time. So a space of constant curvature, which geometry people call as space forms, they are very well known to the geometry people. So in the space of constant curvature, no point and no direction are preferred. That is, the space of constant curvature are isotropic and homogeneous, and thus they find their application in the Einstein field. So one can find out more details about this in one of my book on tensors. Anyway, just to save some time, I skip some details. Next one is the symmetry of the space-time and which is solid force. So here I will show only the results that we have obtained because there is no time. I don't have any time to explain each and every step of the theorems. So the construction of gravitational potential satisfying Einstein field equations is the principal aim of all investigation in the gravitational physics, and this we often achieve by imposing certain symmetries on the geometry that is compatible with the dynamics of the chosen distribution of matter. And how it is done, you have just seen the lecture of Professor Day, that how he has defined the energy momentum tensor. If you look at the Einstein equation, Rij minus half Rgij is equal to K times Tij. Now the right hand side Tij is simply nothing the matter distribution or the energy momentum tensor. So right on the left hand side we have the geometry. Rij is a geometric object, and of course Gij is a geometric object. R is also a geometric object, Richika is scalar. So on the left hand side of Einstein equation we have the geometry, on the right hand side of the equation so we have the physics. So if the distribution of matter is compatible with the geometry, then we get certain type of symmetry. So this is roughly what the idea of symmetry. So the geometrical symmetries of the space-time, mathematically, if we take the Lie derivative of any tensor or a scalar, if that Lie derivative is defined, if it is going to be zero, then we have some sort of a geometrical symmetry. So I will take certain type of geometry, these symmetries which are necessary for my work. So the role of how these symmetries are there in general relativity, it was first introduced in a paper by Kazin and his colleagues in 1969, and then he continued his work in 1970, 1971 and 77. So these symmetries, they are also known as collineations. They were further studied by our group, myself, my student Hasan Ali, my supervisor Hussain, Professor Hussain, and my student Ali Pundir and Su, and Ali Pundir and Hasan. So we have developed this symmetry business to some extent. So far, more than 26 different type of symmetries or collineation have been studied, and the literature on such collineation is very large and still expanding with results of elegance. For example, recently, one of our students, Ali, with his students, Salman, has defined a new type of symmetry. Maybe he will present his paper in this conference. So he has defined a new type of symmetry. So the symmetry business is going on. Of course, we are getting many results. So here I shall consider only those symmetries which are required for my investigation. So first one is the motion. Is the Lie derivative of metric tensor is zero, we call this as the motion. That is, the distance is invariant. Distance is not going to change throughout. So then we have the motion, or this equation number 5 is also known as the Killing equation. Or this is also known as, Xi is known as the Killing vector field. So conformal motion, Lie derivative of Gi is equal to some scalar times Gij, then we have a conformal motion. Special conformal motion, if the Lie derivative of Gij is some constant scalar times Gij, where scalar satisfying this, so we call this as the special conformal motion. Homothetic motion, that is, if the two distances are in a constant ratio, then we have a homothetic motion. Then also we have, there are many symmetries. I am using only those which I require. So while conformal collimation, if the early derivative of y tensor is zero, then it is while conformal collimation. Curvature correlation, if the early derivative of the curvature tensor is zero, it is curvature collimation. Ricci collimation, if the Lie derivative of Rij, that is the Ricci tensor is zero, then we say that the space-time is admitting the Ricci collimation, then affine collimation, the Lie derivative of Christoffel symbol, which can also be written in this way, is zero, then we call it affine collimation, and similarly conformal collimation and spatial conformal collimation. So, since I have only very little time, so just I skip the calculation business, and the first result that we have obtained, that if the vector field xi associated with the Ricci soliton M is our space-time manifold, G is the metric, and xi is the vector field. So if this vector field is killing, then the manifold M is Ricci-fied. This is one result. Another result we have got in the form of theorem 2, if the vector field xi associated with Ricci soliton is killing, then the space-time admits Ricci collimation. And then combine all these equations together, we will have a corollary that if the Ricci soliton is steady, then the scalar curvature is expanding. So this is some physics is also involved here. Geometry and physics are there. Also, we can simplify all these equations and go on simplification. Then we got a result which was already published in 2009. So this result is we will use it later on. So the vector field associated with Ricci soliton is conformally killing if and only if M is an Einstein manifold. So from some results of the book of Yano, the Lie derivative book, we got another lemma. Xi is a conformal killing vector, then it is also a conformal killing equation, conformal collimation vector field. So combining these two lemmas, we ultimately got this result. A vector field xi associated with a Ricci soliton is conformal collimation if and only if M is an Einstein manifold. So while if we use the definition of conformal motion, then we get that if sigma covariant derivative with respect to jk is zero, then the vector field associated with the Ricci soliton is a special conformal collimation vector field if and only if the manifold is an Einstein. Again, using certain equations that we have just developed in the previous slides. So for Einstein spaces, the vector field associated with the Ricci soliton is scaling if and only if it is expansion field. Moreover, we know how to define the homothetic motion. So in homothetic motion, the two distances have constant ratio. While in simply motion, the distance is invariant, it is not going to change. So with these, we have got this theorem number 5.